All right, let's start in on the solutions to the quiz. I'll try to keep it as brief as possible. This will probably be spread over into two tutorials. All right, first question is, what's the criteria for some harmonic motion? First and foremost, you have to have a restoring force. Okay, right, that's just Hooke's law. In other words, the force has to be, restoring means that the force is always in a direction of equilibrium. And I'm just going to write equilibrium as x equals 0. Okay, the second part is, actually I jumped the gun, and this is pretty important, is F has to be proportional to x. Okay, so you can have restoring forces that don't follow that law, but when they're linear with each other, then you have simple harmonic motion, and when there's a negative in there, in other words, F is the direction x equals 0, that's the second criteria. All right, at what position does have the greatest acceleration? Well, if F is proportional to x, then when the amplitude is greatest, or the distance is stretched is greatest, the force is going to be greatest, therefore the acceleration. So you could have put A, or you could have put negative A. All right. Elastic potential energy follows 1/2 kx squared. So again, when amplitude is greatest, you're going to have the greatest potential energy. And then the speed is going to be greatest when you have the least potential energy, or the greatest kinetic. Least potential means when x equals 0. Okay, so that should help us with D or C, however it's on your test, is how do we plot acceleration as a function of velocity. Well, there's three things you need to get right on this one. So I'm going to start conceptually before I go to mathematics. We should understand that when the acceleration is at the greatest, the velocity is at the least. Okay, they're always out of phase with each other, and conversely, when the acceleration is 0, the velocity is greatest and on both sides. So you have to be on both sides of the y-axis. You have to have this kind of symmetry. So that's one of the points out of 1.5. The next question is, how do we connect these dots? Is this linear or nonlinear? The answer is it should be linear. And how are you supposed to know this? Well, we know that A is proportional to x, right? That comes from Hooke's law. That's what we talked about quite a bit. We also know that V is proportional to x. This comes from conservation of energy. If you recall, at some point you might have maximum kinetic, and at another point you have an equal amount of potential. So we see that V squared is proportional to x squared, or V is proportional to x. So if A is proportional to x and V is proportional to x, then it stands that V is proportional to A. Okay, so let's move on. All right, now we're trying to put this into motion, application by looking at a molecule, methane molecule. This actually is pretty important for global warming, but that's not really the issue here. So first question with the amplitude. Amplitude is simply the height from rest position, so you should have had around 1.5. And don't forget over here the units, times 10 to the negative 10th meters, right? Which would make sense for a molecule. You wouldn't expect the amplitude to be 1.5 meters. All right, show the spring constant is a certain value. So what on here can relate to the spring constant? Not amplitude directly, but you could try to take that root knowing velocity, but we don't have that. But what we can do is understand that it's based on period. So the period here is from the beginning to when we're back to this part of the cycle. So we've got to estimate what that period is. So for 3 points, first one is the equation, right? We want to relate period to k. That's 2 pi radical m over k, okay? So we've seen that equation quite a bit. Second point is understanding that the period, getting that right. You have a little wiggle room here, but you should be very close to 0.11 times 10, right there, negative 13th meters. All right, so if we plug this into period, we put in the mass, which is given up here, and you correctly solve for k, and then you should get around 554. Again, you have a little bit wiggle room if you didn't have exactly 0.11. If you had 0.115, 0.105, something like that, that would be acceptable. Next, all right, calculate the maximum speed and the maximum acceleration. Okay, so we've done this quite a bit in homework. The equation for Vmax is simply this, and I hesitate to write it like this because I don't want you to think you have to memorize this. You don't. Okay, this can be gotten from conservation of energy. In other words, the potential energy, elastic potential energy maximum at the beginning is going to equal the maximum kinetic energy when x equals 0. So if I put in 1/2 Ka squared here and 1/2 mv squared here and solve for v, then I get this equation. And if you put in the numbers, so 1 point for, actually a half point for this equation, substituting in the right numbers, 8.6 times 10 to the 4th meters per second, or 86,000, okay? So again, we have K from above. You didn't have to know that beforehand or have to derive that, and mass was given. All right, for A max, we want to use Hooke's law, the second law of motion, right? A is F over m, and F is Kx. We don't need to worry about the negative here because we're just interested in the magnitude, so that's just going to be Kx over m. What x are we talking about? Well, we're talking about the maximum, so A, the amplitude. And we had the amplitude up here, K is here, M is there, so if you substitute the numbers correctly, you should get a very large 4.9 times 10 to the 19th meters per second squared. Okay, so that's 2 points, one for the equation, one for the correct values. Now we want to sketch the velocity as a function of time. Okay, and this has 4 different things we're looking for here. First of all, you want to ask yourself, what is the velocity at time 0? Okay, so if we go back up to this graph, we see velocity indirectly is the slope. So at time 0, this is flat, so we should understand that it's not moving initially. So for half a point, you have this as your first point. Okay, now we can ask yourself, is the velocity initially positive or negative after this time? Again, if you go up to the position time graph, the slope is negative, so we should have a negative value. And we go down as far as the maximum amount, which you calculated a minute ago. So we want to put it down here. Now, to place that point, we got to then at the same time relate it to the period. So we know that the beginning of the cycle is here. We found earlier that the end of the cycle is right around there. Okay, that's at the 0.11 times 10 to the negative 13th. So halfway between them is right about there, and I'm just trying to figure things out. So this is also when the speed is 0 at a half a cycle, so our maximum speed is going to be halfway between these 2 points. How far down you choose to go is arbitrary because you don't have to label the actual value on the y-axis, but we do know that's where the maximum speed occurs, and therefore it makes sense the maximum speed in a positive direction would occur there. So if you show that correctly, there's another half point, and then you just connect the dots and you get what you should recognize as a negative sine curve, which will be important later. So that's 2 points for getting each of those aspects. All right, write the full equation. Okay, so we should recognize this as v as a function of time is negative v max. Okay, right, and it's just really a fraction of this, and the negative indicates initially it's going to be negative times the sine of omega t. Okay, so that's the general equation. If you have that, then there's 1 full point. Now we just got to put in the relevant values. So that's negative. We found V max is 86,000. All right, I'm going to put that sine. And then we want to do omega t. There's a number of ways we're going to do it. I'm going to use the form 2 pi over the period times t, because the period we know. So if I do 2 pi over the period, I actually do that calculation, I get a very large number. All right, 5.7 times 10 to the 14th, times t. So that's all multiplied by this, which I'm not going to rewrite. So there is your full answer for another point. Okay, so next problem is reminiscent of the lab you did. Instead of a mass spring, we have a pendulum, but it's the same idea. You've got t squared versus L that's linear, and we want to know what's the acceleration due to gravity, little g. So what we want to do is we want to take this and relate it to the theoretical equation. So the theoretical equation for a pendulum is 2 pi radical L all over g. So there's the thing we're looking for, and we want to manipulate this so we can relate to the slope. So I'm going to write off to the side, okay, that the slope is equivalent to t squared over L. So when I manipulate this, I'm going to square both sides. So I have t squared equals 4 pi squared L over G. And if I solve for G, basically flip things around, I get G equals 4 pi squared L all over T squared. And so we want to recognize that this is 1 over the slope. So G ultimately is 4 pi squared 1 over the slope. Oops, sorry, I'll just put SLP. You plug in the numbers and you should get 1.6 meters per second squared. Okay, I'm not sure if this is still on a quiz. Where is this most likely? That's the moon. I don't know if you remember, that's what G is on the moon. All right, next is a multiple choice. All right, we have a position time graph. We want to translate that to an acceleration time graph. Okay, the easiest way to do that, rather than go from x to v to acceleration, is to know what the direct connection between x and a is. And that goes back to the very first page, where again, I'll start with Hooke's law. That's really the foundation for all this. F equals negative kx. That negative is important here. And F by second law is ma is negative kx. So we see that a is proportional to negative x. So a graph is going to look at the negative of this. So this is a cosine function. We want a negative cosine function, and that would be b. Okay, last problem, 5. We have a ranking problem. Let me just give the answer. A has the greatest frequency, then B, then D, then C. Okay, none of them are equal. Now, you got to be careful. We want frequency. So the easiest way to do frequency is related to period. We know period, I'm not going to worry about the 2 pi, is proportional to radical m over k. So we also know that period is 1 over the frequency, or maybe I should have written it as frequency is 1 over the period. So in other words, our ranking is going to be based on reciprocal of this. So F is going to be proportional to radical k over m. So if you put in the numbers for this, right, the amount that it stretches is irrelevant. So what matters is the mass and the spring constant. You put them in and you should see that you get these values. You don't even need the radical because both measurements are under the radical there. Okay, so that concludes. If you have questions, please ask on Schoology.